welcome to this meetup. I think it's the first of the year. We've had full focus on the conference since the pandemic. Really happy seeing you all here today. I'm Jacob from Gaia, one of the founders. And I don't really have much to say more than welcome you and handing over to Tenfifty.
Thank you. And thank you for letting us host this event. I hope you're all enjoying it so far. Quickly about Tenfifty, we're a smallish AI company. We do optimization, and prediction on all kinds of data, which is of course really fun. So please consider us when you think of a new career. Yeah, let's get to the show. So I don't know if this reference is too old, but we're going to talk about base or alkalis and acids today. It's a project we did for Södra Cell down in Värö near Varberg. And they do a, this is their plant. They make paper pulp, not actual paper, but the material you use to later make paper. So there is a sawmill here as well, but all the bad stuff from the logs that you can't use for wood, or lumber, or timber, or making a house, it goes into this process here somewhere, and it's mixed with chemicals and made into a fine pulp. And then I guess at this end there is the completed product, which is dry, like sheets of something similar to paper. And we are, of course, focusing on a very small part of this process, which is somewhere in here. They use a lot of chemicals, and there is, when they have been used, they are dumped into a tank or pool, and they are some of the waste is alkaline, like have a high pH, and some is very sour or acidus with a low pH, and the idea is that they will cancel out, and then it's going to a bioreactor where bacteria eats up all the bad stuff, and then we can reuse the water and everything. But the bacteria are really sensitive to the pH level, so the level needs to be within a small interval. And the problem is, so to adjust the pH level, they add some other chemicals, either an acid or a base, to adjust the level. And the problem is how much to add, and of course you want to add as little as possible to save money and the environment. And to know how much to add, we need to know the pH value of the combined stream, of course. But their problem, now we get to the core of the problem here. You can't, if you put a pH sensor there, it will clog almost immediately, and then you can't get any readings. So you have to stop everything, go in and clean it with some chemicals or manually, I don't know. It doesn't work. So our task was to develop a soft sensor that can basically calculate the pH value based on the stuff we put in the tank. And if you notice I am struggling, it's because this project was a few years ago, so ask questions if something is not making sense, and I hope I remember the answer. So here's a schematic of what I just described. So here we have the tank where everything is mixed. There are two waste streams. The AA is alkaline and the AS is sour. And they go in here, and then we also have the control chemicals going in here. This is the sensor that doesn't work because it clogs. And then the mix goes into a cooling area. And then, as luck would have it, one of these sensors over here, or a bit further or closer to the bioreactor, which is over here, actually does measure pH value. So we have a measurement we can trust to learn from. So the features we have to learn from the data is the amount of waste coming in both streams and the pH value of both of them. We also know if any of the control substances were added, and we have like the level and the temperatures and also then pH value over here, because as luck would have it, they don't really trust their existing system, so they have a second control system for the pH value after this. So the data looks like this. We have the data, this is not the entire data set, but it's still a little bit squeezed. But basically, the pH value varies around 7, which is the target value, of course. We have the value at 20-second intervals, about 600,000 measured points from basically a year. Or we were training on 600,000 points, and we have a test set of 200,000 points, which is the end of the data set we have. So the first thing we did was to figure out how long, let me go back, how long time, because we want the pH value in the tank or just after, and we have the target data we have over here, assuming that the pH doesn't change over here. So we just need to figure out how long time does it take for something flowing out of here to get over here. So then we just did some simple statistics. This is a Spearman R correlation between the target pH value and the different, like the pH of the alkaline, the pH of the sour, and the flows. This one. So we want maximum correlation, and it happens here about 20 minutes in. And of course the green one is anti-correlation or negative correlation, because it's low pH. So that's just a quick check that, yeah, it looks like 20 minutes is reasonable, and that's also what the guys at Södra said. It takes probably 20 minutes. Another problem is common in these industrial processes. They are running a long time with everything's working fine. We're just adding the same stuff. There is no disturbances. That means we get a lot of data that is the same. It doesn't add any information to our problem. So we did stratified sampling, where we grouped or clustered the data points. So this is the pH again, but the clustering is based on all the input data. And as you can see, the purple cluster is by far the biggest one. But then for our training set, we just picked an equal amount of data points from each of the clusters, of each of the colors. This gives us a few advantages. It's a lot faster to train with less data, and it's also more robust because it's not overwhelmed by one steady state cluster. And in this case, we used HTTP scan to cluster, but of course you can, the statistical method of stratified sampling is applicable to any grouping of the data set. So now we're ready to model. And this is where the project really took off, because the guys at Södra really wanted to learn how to do this. So they gave us, we could do whatever we wanted, as long as we told them what we were doing, which of course was very much fun. So we always start with boosted trees. So here, as you can see, we've changed to predicting the change in pH instead. So it varies around 0. And so this is a small test data set, but it looks pretty good. No? We capture most of the dynamic. And when we started the project, Södra said that if we are within 0.5 pH limits, they would be really happy. And this is the mean average error, mean absolute error is less than 0.1. So obviously we solved the problem. But we can't stop here. We want to try more things. And one of the things that you have to try is neural networks. Everyone expects a neural network. We actually tried a convolutional neural network, which, I mean, it's really common for image analysis. But instead of an image here, we decided to use the inputs. There are 6 of them in this example of the pictures, and then a 40 long time sample, time window. And the details here aren't really important, but we convolute them down to and can make a prediction, and the results are almost exactly the same as for the tree. This one is, of course, a lot more complicated to build. I mean, there are a lot of parameters here that you don't have to, but you can fiddle with. And I mean, there are parameters for boosted trees as well, but mostly it just works out of the box. So in this case, I think this solution might be a bit more robust, but the trees are a lot simpler to build. We continued, of course, as I did. Some of you might have reacted to the fact that chemistry is not magic. There is, if you talk to a chemist, they know what happens to the pH when you mix two liquids. And so we tried a few different modeling types where you can add this information into the system. The Gaussian process is about finding a measurement of closeness to your samples. Graphical models is really about closely modeling the causality in the process, and that's the models that are where we have most of the chemical knowledge in the model. We had actually had a chemist on the team working with us, so that was really, we spent a lot of time on that. And we also built a lattice model. There's a package in TensorFlow that allows you to specify that, okay, when this feature increases, the result will probably increase, and that's information we have. We know that if the pH of the alkaline waste increases, then the output from the tank will also have a higher pH. The problem with all of these, or challenge, is that they don't scale well with data when you train them. So we we had to downsample the training sets, and it still takes a lot of time. What you gain from that is, of course, a more robust model, as you have said, added the prior knowledge that these are the dynamics we expect. So if you have inputs you haven't seen before in the training set, the model should be more robust to those changes and still give you good results. You also, because you add prior knowledge, you have a better idea of what the model is actually doing. The trees and the neural network, of course, they're a black box. You don't know what's happening inside unless you do a lot of analysis. And since these work with, or at least the top two work with probability distributions, you also get, with the output, you get like a distribution of the output. You know how, in what interval can you be certain, or how certain can you be that the output is in a given interval. Let me illustrate that with a short video. So this is the output of the, graphical model. So the prediction is here. This is that's the that's the actual outcome. This is the future outcome that we don't know, and this is the prediction that we are making. And you can see that right when I pointed here it went off, but otherwise we're usually in this high probability area, and then depending on what uncertainty you can accept, you can have a better, a wider, smaller prediction. And here is what's happening on the input side. So I was probably in the way when the base started to increase, and you should see that the prediction soon after started to wear off. So there was a problem also that the system wasn't as, so there are two problems. One is that the illustration schematic we had wasn't fully complete. There are other streams of waste coming into the systems that we can't really, that we don't know about. So you can see here there's a big change, and then the model comes right after and actually capture that pretty well, I would say. The other problem is, of course, that we're working on a system with live data. They are producing pulp, and they can't just shut everything down and let us play with the system. So at times there are different amounts of control acids being added, or chemicals, the acid or the base. Oops. Please ignore what's happening. Now you can see it. Yeah, so these control substances are added, making the data a little bit hard to interpret, because at the extreme points, even though there's a lot of say base waste coming into the system, the people running the system know this and add a lot of control acid. So the pH value can actually go down, even though the alkaline waste is increasing. So there are some inconsistencies like that that are really hard to model using these models. But the graphical model should be able to handle it. So let's talk about model choice. All of these models perform equally when we look at like error rates, or mean absolute error, or root mean square error, or we even designed a special error measurement that focused on areas where there's a lot of change, but the results are extremely similar. So we have to look at other aspects of the models, like the robustness, if the data is changed or different from the training set. Obviously, the trees don't handle that well at all. Neural networks might, the graphical model should. And this part with the uncertainty can be really important in some cases, especially if you want to do control based on these outputs. It's really nice to know, is the model certain that this is happening, or can it doesn't know. Can we change it? Can we adapt it? These are important things for people working with the model in future, of course. And if you can train it and run it. Like the boosted trees with stratified sampling, I can train it in 20 seconds on a laptop. But the graphical models takes days if you're not careful. And of course, if they use memory or GPU or some other special hardware or anything. I don't know actually. I think they ended up using the boosted trees. Anyway, I think that was it for me. We are hiring. Feel free to visit our website. If you have any questions, I'll be happy to answer them.
So I have a question.
Sure.
So the prediction is the pH, but they need to the persons who are controlling the pH, they need to add acid or alkali depending upon the prediction, right? To keep it in the place.
Yes.
So what exactly they were doing after the prediction of pH? Which one was the control of them?
I'm not.
So the question is that the pH prediction is like coming 0.1% of the real data.
Yes.
Now the question is they are now adding certain things to the alkali or acid to make
Yes.
sure that it doesn't go beyond that value.
Yes.
So like some kind of reverse looking into the pH control and how much they need to add. So that part is done into that part also or not?
So that was supposed to be the next step. Unfortunately, we ran into the rebuilding of the plant, so we never got to implement the control part where we take our prediction and maybe an estimate of what was coming in and deciding on how much of the control substances to add. Because that's of course where the real gain of this process is, if we can optimize the use of these substances. But that was never unfortunately not part of this project. Thanks. Sure, yes?
Yeah, the data looked extremely noisy. I can't understand how it could go from 11 pH to 5 pH within I don't know if that was seconds or if it was...
Yeah, so it's... let me back up here.
Earlier.
So...
It's earlier.
Yeah, okay.
Yeah, so that one, yeah.
This one is not.
Yeah, so it goes from 11 down to like 4.5.
Yeah, so the scale here is megaseconds, which is
It's
really
megaseconds.
easy to think about. So that's it's very squeezed things.
Okay, yeah.
But it's also
Okay, I
sorry,
understand the
it's-
time scale now. So.
yeah. So but there is the processes are very noisy. So all of a sudden there could be a big splurge of one of the waste streams, and I think the people managing the control knobs manually for the control chemicals were probably a bit fast and loose with those substances as well. Excellent questions.
So is that how it's done today? That someone just manually tweaks the info of
Yes.
different control substances?
Yeah, so they have basically the same input that we have on their control screens, and then they also have because here at the where we get our measurement, which could be maybe this one, says pH, or somewhere here. After that is a second control step, so they don't have to be perfect here. And then they look at this. Oh shit! There is a lot of this stuff coming. Let's add some of this stuff. Yeah, basically freebasing it.
Okay.
So I think there is a big opportunity to save on these chemicals.